In this video, we are going to talk about AirPods and what is inside of these AirPods, how they work, and Markus is going to explain all this acoustic and technology because he's the expert for these audio devices. Is it correct, Markus?
Yeah, thanks, Robert. Yeah, I'm not sure if I'm at all an expert for audio devices, but I've dealt my life studying acoustics, doing MEMS sensors, and yeah, 10 years of experience in acoustic and also developing some parts of those, not those headphones, but other headphones. So yeah, I'll try to explain what all is in there and what type of engineering and system design went in such a product, because I think, yeah, there's so much value and to learn from that it's worth to have a look today, maybe.
Okay, and I'm going to explain, or I'm going to say that everything what we are going to talk about, it's not like really secret because all these kind of patents are available for everyone. People can check it. So yeah, we will also have a look at the patents. So, you know, we understand better what is actually behind some of the things inside of this. So, okay, let's jump to something specific. I'm very curious what is inside.
Yeah, you're very curious what is inside. So then let's have a look at what is inside. So I think we all know the outer design of the AirPod, and for that let me just show like this. This is the right side of a normal AirPod, and this is the part you stick into your ear. It's called a TWS. So it's a headset, a wireless headset, which you can put into your ears. And I think we are all familiar with this, and we all know that. But I think there's more inside than what we first thought, and maybe this slide already shows it. So in here, in this housing, there's of course what we all expect to be a speaker that can produce some sound and that creates the music or the speech or whatever we want to listen to. But I think in all there's much more to show and to find in there. And I think also this picture here in the middle shows all the technology that is in there. It's not just like a little white housing with a speaker here. There's so much more because it also has to cover so much more, so many more functions in there that we need a really, really complex system.
Okay, so I would expect there is a battery. I think that's
Exactly. There's a battery that's in the stem here.
okay.
They
Then
use
Bluetooth
the
chip.
stem for the battery.
Yeah.
Exactly. A 39 milliwatt hour battery in there, lithium polymer accu, to power the AirPod, which is also crazy. If you think about it, that the design dates back, you could buy them like 7 or 8 years ago, but they started designing this in like 2011, 2012, I guess. And if you think about the battery technology back then and this time, then this is already a incredible thing to have such a battery in here integrated. Yeah, so that of course you need to power the whole system.
Okay, then I already mentioned the next one is the Bluetooth chip.
Yeah, the Bluetooth chip, this is something we, or at least I, don't know a lot about because this is the Apple W1. That's a chip that is only in the AirPod 1. They switched to another chip in the AirPod 2. And this is a really special thing also back then. You have to see it also back then in 2011, 2012, when Bluetooth technology had to be low power. And that was far from easy. And you also have to have the high data rates for the AirPod to have a data signal with the high quality and high frequency rate transported via Bluetooth in a low energy way. So they had their own chip that could do their own magic. I personally don't know exactly what is in there. Yeah, but that's the main chip from Apple, the only Apple silicon in the AirPod One.
So where is the antenna on the picture? I see it in between the components, but where it is placed?
I think we can see the antenna in another slide a little bit better. The antenna is basically folded here. So the antenna has two parts. One part is this one, and the other part is on the other side. And this is like it's a antenna on a flex PCB. The flex PCB is used as the antenna, and they have two parts of the antenna folded up here coming from the bottom.
This is very interesting because it is actually about the battery, correct?
Yeah, it's around the battery. So they have two sides for the antenna, one and the other side to have a good antenna for a directivity in all the directions and not just having half of it covered by the battery.
Mm-hmm. Okay, then I see there is processor and audio amplifier. So why do we need also another chip? Why do we need processor? Because I guess there is much more going on, not only the speaker.
Yeah, there's much more going on. I mean, if you think about what you can do with your AirPod, you can of course listen to music. You can have phone calls. You can tap your AirPod to stop the music playing, start the music playing, and you have some audio processing. So if your audio signal comes via the Bluetooth chip into the device, into the system, it has to be converted to an analog signal, basically. And therefore, you have to decode the compressed signal and then convert it to something that you can amplify in your amplifier. And also for the amplifier, it's a Class D amplifier. So it's looking for, it's per definition, it would be a digital signal, but it's not an analog signal itself. It's like a kind of a PWM signal, PDM signal going into the amplifier. And so the amplifier amplifies the signal to up to like 1.5 volts for the speaker. And it also has to be very low power. You all know, like your big amplifiers you have at home for your home Wi-Fi, hi-fi thing. They are all power hungry. They all get hot. And you have also some headphones with Class A or Class AB amplifiers, and they went for a Class D, so the digital way, to have a very low power way on getting the audio signal out. And if you look closely, you see a Max. This is not made by Apple, and this revision, it's still a Maxim, or I think they are now Analog Devices nowadays. So this was a chip from Maxim back in the days.
Okay.
But also customized for them. You cannot buy this on the open market.
Okay. What I'm curious about, okay, I know I would expect there are microphones. We will talk about microphones a little bit later, but what about the accelerometers? So these are for the tapping?
Yeah, there are two. Actually, there are two accelerometers. They are sitting here. One is here, and one is on the other side of this PCB. And they have two different specifications. One is good for getting higher frequencies, and the other one is targeting to very low frequencies. So with high frequencies, I mean like up to 2 kilohertz maybe, and the other one is maybe like up to 100 or 200 hertz. And this means they are for different applications. The low frequency one is for they use it for the tapping. If you tap, it gets an impulse and they can sense it. But I guess also for like motion tracking, like when you move, you also have a accelerometer in your phone, for example, and when you're outdoors and you're moving, they can see, okay, does this fit together? All this stuff, which is not disclosed, so we don't know exactly what they really can do, but this is for the low frequency accelerometer. And for the high frequency accelerometer, it is to detect speech. It's also sometimes called speech accelerometer. So if I talk and I have the AirPods in my ear, you can also have the sound. It conducts through your bones in your face, like it goes through the bones here and comes through the ear into the AirPods. So they are vibrating while you are talking. And so they can sense if you are talking, and to some extent also get the audio signal of the speech. And this is very helpful to detect if it's just random noise from the outside, if you're talking to someone, or if you are the one saying, hey, Siri, do something. And that's why they have those two accelerometers in there.
That's interesting. I would be thinking they use microphones for this, so that's interesting.
Yeah, they actually do. If I say, hey, Siri, they use the microphones to detect this. But it's an additional source which is very dedicated to yourself. So if someone else is saying, hey, Siri, then your accelerometer will not sense anything.
Yeah.
So this helps. And the second thing where I have to say I don't know exactly what they do inside there is about power saving. Your microphone is very power hungry because you have to sample it at a very high sample rate. And then you can also use the accelerometer to like, if you detect something, then shut on or off the microphone to be used. But yes, you're right. They also use the microphones, of course, for the Hey Siri part.
Okay, proximity sensors.
Yeah, there are two. And if you look at your AirPod, there are these little black dots. You have so there are openings like this with meshes, and there are other openings with the black dots. And behind the black dots, there are proximity sensors. A proximity sensor works like this, that you send a light signal, or basically you send light and you measure it back. And if something is in the way, then you get a reflection of the light and you can see that there is something. And for this, they have two. One is facing towards the ear and one is facing, actually, we can see this in a later sketch. Maybe I go here now. We can see this here maybe a little bit better. So one is here and the other one is on the other side. And they are, if you insert them into the ear to detect where they sit in your ear, and they detect those two parts. And from this, they can see, okay, I'm in an ear or I'm not in an ear. And then, for example, stop the playback if you take them out, or start the playback once you put them in.
Okay. And so what left? The microphones.
The microphones, yeah, there are two. One is up here and the other one is down here at the very bottom. These are MEMS microphones. Also, again, crazy technology for the time back in the early 2010s. And they are used for everything you could imagine, for speech and telephone calls and, you know, as you would expect. There's also, especially in software, a lot of things behind the microphones. Because you have to do beamforming and echo cancellation, for example. So if you have here your microphone and you imagine they are sitting like here, and then your sound comes from the outside, they can measure this. But if you are talking, then they measure everything, but not your voice. And so based on this, they have two, one is here and one is here, and then you can do beamforming. That's kind of, okay, when is the signal coming to here? When is the signal coming to here? And with that information, you can kind of get the origin where the signal is coming from in 3D space, or basically in 2D space. And from this, you can be more clear for phone calls and so on. So.
Okay, and what are the other parts what we were not talking about? System test, that looks kind of...
Yeah, that's, if you look here, you see this PCB, and what you see here is the backside of this PCB. And this PCB is glued on the backside of the speaker. And if you like separate them from each other, you will find this. And these are just a lot of test points for system tests. So when your PCB is fabricated, you go in your test environment and you have your needle probes, and they conduct all of those points and measure all of the electric values you have on your PCB, power rail, digital readouts, and so on, to like verify that your PCB is working as intended. And so they integrated this on the backside, where they also glue the speaker on, like on the backside of this PCB. And thus I call it system test.
Okay,
yeah.
And the acoustic volumes and meshes, and this all is important to improve the quality of the sound, or?
Yeah, right. Or at least have some sound there, right? So if you just put the speaker in there and nothing around, you won't hear anything. You can try this with your loudspeaker. If you have a loudspeaker and you just take out the driver, so the speaker itself, and you power it in the free air as a block, you won't hear anything, especially for the very low frequencies, because just the sound goes around from the front side to the back side and cancels each other out, and that's it. And to make the AirPods sound as they sound, to have a good sound quality, yeah, all of this engineering around here has to go in there. And yeah, it's a lot of engineering. It's expensive. Not just the engineering, also those parts are quite expensive, also those meshes and so on. And yeah, also a lot of engineering in the volumes, because there's a designer who tells you how this thing has to look like, and then there's an acoustic engineer who says, but I need a big volume and I need it shaped like this. And so you have a lot of fights about where to place them and if they are too big, too small, and function versus design in the end.
This is interesting because I would never, if I would be building something like this, I would just put their speaker and I would be like, oh,
Yeah, right.
does
And I
something.
mean, there's a lot more. I mean, I wrote down just a little few things. I think we made it through all the obvious things, like it has to play sound, there has to be some Bluetooth, it has to run for some time from the battery. You want to do phone calls, you want to do tapping. Active noise cancellation is not part of the AirPods, AirPod 1 and 2 at least. But there's so much more to think about when you assemble all of this. Like you have to be able to produce it. You have to be able to have your safety standards. You have to be able for your IPX rating. So
It was
if
actually
there's
one of
water
my
coming.
questions, because it looks like you disassembled this one. Did you?
Yeah.
But I would expect it would be like kind of sealed and it would be like super hard to disassemble.
Yeah, it is sealed. You have to be a little careful with taking the things apart. And yeah, so I disassembled this one, and you still see, so the front set was sealed, of course, but not potted, so it was not like filled with glue. You cannot fill the thing with glue because then you don't have any acoustic volumes anymore. But you see also here, the black thing here is some silicone rubbery glue that was put in here for stability reasons and for, all the other things, like also temperature, humidity, stress relief, everything you can think of, which went into a system engineering to have in the end a system that is working and not just doing those obvious 5 things, but going through the whole production line and having good acoustics, but also surviving, for example, the washing machine. You can throw them in your washing machine and they should, in theory, survive. And you can drop them and they should survive. And you can leave them in sun in the car and they should survive. And they should also survive falling into the snow. I mean, you have acoustic parts here that get warm. They are like 20, 30 degrees, and then they fall into the snow, and then they are like minus something within a few seconds or minutes. All of this has to be implemented into the full system. What I recommend everyone who's looking for a device and trying to learn about, search for the FCC documents. You can find them online in the internet for nearly all the devices. They are publicly available. You can learn so much from the FCC testing about devices. And of course, they also have to have the FCC for Europe. They have to have the CE. Also this is EMC, this is safety, and so on. So there's a lot of things that goes into that, and in the end, it has to look nice and work and be cheap.
Let's have a look on the patent. I'm very curious what they had to patent on this one.
Yeah, I mean, there's not just one patent. I have here taken the images from one patent where they have those images in. But I think there are like, I haven't counted them, but at least 5, maybe up to 10 or more patents concerning the AirPod. And they all share some parts, and every patent has also its own main point, what they want to accomplish with what patent. But if you have an Apple product and you want to learn about Apple products, look in their patents. They are really like comprehensive. They have good drawings of their actual devices, probably for also freedom to operate. And they show what's in there. And I have here, these are taken from the patent, and I have put some notes on that, what it is, and put some photos on it. And as you can see on the left side, you have the drawing from the patent, and you have here the what you can buy in the end. And this is really what you kind of find inside. So you don't need to disassemble them. You just have to open the patent and see what is there and why it's there, and you can read everything. And they also show their PCB. Like this is the drawing in the patent of the assembly of the PCB. And this is what I got out of the AirPod as a PCB. And there, you can do matching. Behind here, there's the main PCB with the processor. There are the accelerometers, there's the proximity sensors, the accelerometer from the other side. So you can just, you don't need to disassemble. You can just look at it and see what it is. And also here, by the way, this is the part of the antenna. So this bottom part is used as antenna, basically.
You know what I'm thinking about is like how they can patent this, because if someone else would like to build something similar, basically they have to build something similar. So
yeah, but they don't patent it. They don't patent this, what you see here exactly. They write a patent, for example, about the proximity sensor, that it can detect the concha and the tragus of your ear. And then they have all these pictures in there. And then they write another patent where they have the tap detection, for example. And then they have all these pictures in there. And so they have like many patents where you can find usually those pictures you find in all of them. But if you want to learn about how the tap detection, for example, works, you can find the patent and read it in there.
Okay. So how if someone is interested to search for these patents, how do you search for them? Is there a website or?
Yeah, basically, you can go to any patent searching website like Google Patents or eSpace.net or anything.
Can we show it? I don't know.
Yeah, sure.
Just an example. So
let's open Google Patents. Shift it to here. So what do we want to
it's like patents.google.com. I had no idea something like this exists.
Yeah, exactly. And I mean, let's just search for, that would be the easy one. Search for Apple, search for headphone, and see what comes up. And then you can search through them. And basically, if you want to really learn about things, you have to be more specific. Like search for the tap detection, and then you can search through all the patents and see what you get. This is the harder way. The easier way is you go there, you know something you are looking for already, and you can search for this. And then, you end up with this patent here is the patent called Earbuds with Acoustic Insert. And you can read through the patent. You can read through the claims they make in their patent. You can download your PDF. So that is basically then the patent you can read through. And you see the pictures, you see a lot of references, and then you should come to the script, or first the pictures. We should also see the picture which I have shown in the slide at some point. I don't know, don't remember which number it was. Yeah, you remember this. This is what I have shown. And then you can start searching within the patent. Say I want to learn what the 3205 is, then I just search in the patent for 3205, and then I learn it's the driver, and you can learn what this all does and why it exists. And once you have learned about this or read about this, you can also see what else is related to this. This is usually shown in the, I go to the very bottom now. Here you can also see what else is there, what are the, like here, what are the references, what are other patterns they reference. And then you can start, doing a full research on who referenced this, whom they referred to, and read it and learn really a lot. I like learning from patterns. It's the best documentation you can ever get.
Interesting. You know, I think like last week or a couple of weeks ago, I actually read they Apple patented something new for the next generation of AirPods. They would like to integrate like sensor, like I think electric sensors or something, and measure all the kind of things through the air, through your ear.
Yeah, they want to integrate sensors that can get you the magnetic and electric fields emitted by your brain, basically. Because around us there's just an electric magnetic field made by our little brains, and then you can try to get the signals and do stuff with it. This is what's coming not only for Apple but also for other headphone manufacturers. And there are a lot of patents coming out right now in this area. It's a little bit scary, I have to admit, but
I was actually thinking about this because I think right now what they need to do is put their sensor and then use this kind of machine learning or something, and then they will, who knows what they will be able to detect. They will find out once they have all the data.
Yeah, I mean, there's big research in that topic, and they are about to include this. And once you see that they are about to include this, then you know that they already have results on what they want to do with this. This is not just like a research in progress. This is already like building on the research that is there.
Oh, okay.
Yeah. So, but that's coming in the next years for sure.
Okay, so let's move to this simple one. We skipped some
it's a very
slides.
simple
So what
one.
do you have on the previous slide? Yeah.
So what I wanted to do here is because I think that's a very nice learning for like a lot of people. It is for when you start designing such a system, such a complex thing, then you start thinking in requirements. You are not just, okay, let's take a driver and let's assemble it together, and in the end, one day we will be finished. It's more like there's a product management department which says we want to have a headphone that, for example, plays sound in a very nice sound quality. And this is called a product requirement. Some call it solution requirement, but product requirement would be the right term, I think. But if I tell you, Robert, can you please go and make a very cool sounding headphone? Then you still don't know exactly what to do. You're like, okay, what does the sound pressure has to be for low frequencies, for high frequencies? What has the THD to be? What are my constraints that I'm working with? And so what you do is you take this and you convert this into functional requirements. So you say, for good quality, I want to have this sound pressure level over the frequency. And then you formulate this as the sound pressure level over frequency shall be within a range. And this is what you do for the main functional requirements. And for something like the Apple, this would be a document with hundreds of pages for all the requirements they have. I mean, you remember the previous slide here, when you think of what all this thing has to accomplish, then you break it down from the product requirements to functional requirements. And this is what you give your engineer. Dear engineer, please select a driver that can do a THD that is so low, and please select a driver that can do at least 105 decibel SPL. And please select also a amplifier and analog to digital to analog converter that can do a minimum 40 decibel SPL without just having noise in there. And all of this comes together, and this is how you basically take this complex thing and break it down. And what I have prepared for today is like, we will just have a look on a very small thing, like how do we do the sound? How do we create the sound in the Apple AirPod? But actually, that's a quite really huge and big topic. And that's what I wanted to show here. And I work with also startups and smaller companies, and that's a very high recommendation I give. Think about your product, think what it should accomplish, and then start like, okay, what do I have to build to accomplish what I want in the end?
Well, I can imagine. So, for example, when someone asks you to design headphones or something, you would not expect like, I would like to have headphones which can play great sound quality, but you would like to get this kind of specification, and then when you deliver your work, you will say, check, 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 check.
Exactly. That's what the engineer in the end has to do, and that's where the system architect comes in and has to build or the requirement engineer and has to build a requirement sheet so that he can tell the engineer, build something that can have this range, because then we can sell it and it is allowed to cost whatever. And also the yield, for example, they also specify you some yield, like say 99.5% of the devices have to work in the end and not fail production tests in the end. For example, this is just an example. This is not a real world number. They are a tiny bit different. So this is how you start defining and breaking these things down. And that's also, I think, when we are talking about such a product, we have to keep this in mind. And also when we criticize such a product, when you, for example, say, okay, I don't like the sound quality of the AirPods, then you might have to also think about why the sound quality is like this. And what else did they have to fit in there to have the full system running, which you maybe on first sight don't know. So that's also often, I think, a very good reminder to people to pay attention to what are all the cross correlations between all of this.
Okay. So what do you have on next slides? The next one, we already had the number 6. Okay, number 7, yeah.
Yeah, so we went, maybe just short, we went through this. If you want to take track, you can also have a look in the patterns here. But one which I want to emphasize here, which is also really great, is the engineering behind the main PCB they have in there. So this is a assembly of 2 PCBs. There's a little connector in here. And I mean, you have designed PCBs, a lot of PCBs in the past, and you know how difficult it is to, first of all, design a PCB that can do all of this with analog, with digital, with wireless, with antenna integrated, and so on. And then there's a designer who tells you this has to fit into this housing, and you know it has to survive all the environmental requirements, like cold, like it shouldn't do any humidity things in there, and so on. And then you come up with like this part here, this little part. I found this so cool because this was folded 4 times and packed into like this little area here, just to have a strain release in every direction and to have it to be able to even assemble this. And also down here, I didn't disassemble this, but if you take this apart, you will see that this is folded like 4 times in here, one like forward, backward, sideward, and then you have the connection to your battery charger for strain relief, for manufacturability, and all of this is done by the engineers. And yeah, I find this remarkable.
Yeah, I agree. I think this is probably one of the reasons why these CAD softwares are becoming more and more complex and supporting all these flex cables, because these flex PCB designs, they are actually quite important for some companies.
Yeah. And I mean, this is like, I think they started building this like 10 years ago, right? So I imagine the software back then. So I found this remarkable when I saw and disassembled it, and how much detail is in there. Just for, I know there might be a lot of people who are happy to see the boards in here. So I just, these are the disassembled boards, and I marked where I know what is in there. So we have on one of the boards, this is one board, backside, front side and backside. And I marked what is in there. You have the Apple W1 chip on one of the boards, which is directly behind the transducer. Or not transducer, behind the driver. Then you have one board which holds the amplifier, the accelerometers, and I guess this is some low dropout regulator, but I'm not 100% sure. And then you have another board where I personally don't know exactly what is going on. I didn't try to
So there are
rework
three
what they are
PCBs.
doing. There are three PCBs, and you can see they are like folded, like behind each
Or
other.
basically, it is one PCB, but they are there are three areas on this PCB.
Right. It's a widget flex PCB connecting all of the three PCBs with one flex cable, basically. Yeah. And this is, I mean, already to design this, I think is great work, taking the time when this was built into account. Nowadays, this looks a little bit different. If you look on newer designs for such headphones, they started integrating a lot of things into one, like I would call them one big black plastic piece. So they have a in here like a system on chip where they have usually many of those chips integrated, like the amplifier, the Bluetooth, the DSPs, and so on. That's where the trend is heading towards for power efficiency, basically, and for better integration. Yeah. But I think with this, we covered mainly the like non-acoustic, like obvious non-acoustic parts. There's so much more, but you know, there are better experts out there than me to cover all of this, I think.
So now we are going to the area where you are the expert, the acoustics.
Yeah, kind of. I mean, I've been working on MEMS loudspeakers the last few years, and so I also had to deal with some of this and understand all of this. And so it was kind of easier for me to construct what's going on in there. And I thought it's maybe also valuable for a lot of people to maybe learn about acoustics, hear about acoustics. And there's also like acoustics also origin from the electrical engineering. So there's a lot of like cross knowledge between both of them. And I thought it would be also interesting.
Yeah, let's do it. I'm very curious.
So that's like basic acoustics class. You have your ear and you have your true wireless earpod in here. And what you have is, from an acoustic point of view, maybe let's start from here. You have the eardrum, and until your eardrum, that's your ear channel. So until here, everything is air, and then after the eardrum, okay, behind this is also air, but then like the bone conduction structure starts, and then you get into your inner ear. But if you think about what is air and what are air volumes, we are here, and the sound comes from the headphone to your eardrum. In your headphone, you also have a little bit of air, and then you have the main part, which is here marked in yellow. This is the speaker, so the speaker membrane. And behind the speaker membrane, you have a back volume, similar to your loudspeaker that you have in your hi-fi system. You have the box behind your speaker or around your speaker, the little volume. And this is what basically defines every headphone you find out there in the market. So if you draw this in a more easy way, you have your back volume, you have your speaker, you have your front volume inside your speaker assembly, you have your ear channel, and then the eardrum. And here you can say, okay, the sound pressure here, this is what I observe as a listener. And then, as I said, it originates from the electrical engineering to some part. What you also can say is it's the same like having a volume, which is like a capacitor. You have a source, which is your speaker. You have another volume, which is another capacitor, and you have another volume, which is this capacitor here. And what you have is you have an excitation. This would be like the equivalent of a current source or a volume flow in the acoustics. And then you have your sink. This is the voltage or the sound pressure on the end of your ear on your eardrum. And this is how you easily can model all of this, what you see here on the left as a very easy model to understand. And I think that's a very clean way of starting understanding how such a acoustic assembly basically works.
I had no idea you do this kind of models for acoustic. I could imagine you need to do some kind of modeling, for example, when you are building, I don't know, some kind of church or something, and you need to be sure there is going to be good sound, or theater, yeah. But that you also model this kind of like super small situations, I had no idea.
Yeah. Especially for the super small situations, it's quite easier because you have plane wave radiation. And as long as you have plane wave radiation, then those models hold. If you have radiation into free space and have maybe radiation patterns or so on, then this might be not 100% true anymore. It's the same for like antenna technology, for example. As long as, or for waveguides, as long as your waveguides is small to the wavelength you want to get through the waveguide, you can work with this. But if your waveguide gets large compared to the wavelength, then you have to start a little bit more complex stuff.
Okay. I'm just curious.
Yeah.
So why do we need this back volume and front volume? Because without this, the sound is not going to be good.
Right, exactly. So maybe let's have a more a deeper look here.
Okay.
Then this would be like the step, the intermediate step before it's easy to explain why we need a front and back volume and all this stuff. So what I did here is I assembled a little bit more complex acoustic system, which is still your headphone inserted into your ear. What we, in addition, did, we plugged in the outside world. So there's, of course, from here air being able to escape, and we have to deal with the infinite volume of the outside world. And in here, I said there's an eardrum, but I mean, there's still an impedance of the backside. Your eardrum is not like a rigid thing that doesn't move. It has a certain acoustic impedance. It's kind of soft. And so there are definitions on what you can place here as an impedance to work with. And then if you take this into account, you can build your whole system starting with your audio signal. Then you have your PWM signal for your amplifier, for your Class D amplifier. This you give into your speaker coil. Your speaker coil converts via Lorentz force your current basically into a mechanical force, and your voltage it's basically a all-in-ones, like your forces convert into a mechanical force into the speaker membrane and into an excitation into the speaker membrane. The speaker membrane has a loss, a mass, and a stiffness that you have to move, which you can include also here in a mechanical way. And then you have your force and your displacement. And the speaker converts on the surface to a volume flow and a sound pressure. And then we have what we saw basically before. We have a back volume, we have a front volume, we have a leakage to the outside, we have your ear channel volume, which is the thing in here, and then everyone calls it IEC 711 coupler. There was many years ago, people started characterizing the impedance of the inner ear, and they started coming up with a replacement circuit. And this is the basically replacement circuit for the impedance of the inner ear. and everyone is using this right now.
Why is it important to know this impedance of the inner ear?
Because you want to know what is the sound pressure level over frequency. In the end, to model all your volumes inside here, and to know what is the sound pressure level here inside your ear, you have to take all of the impedance of what is coming in here into account to really say, okay, I have here this this sound pressure level. It's quite different to the normal thing. When you come from the outside, you have a big loudspeaker in front of you, and then your audio signal is coming from the outside. Then your audio signal doesn't actually care on what is going on inside your ear. It's just there and creating a sound pressure because your source is so big. But since we are here in this very closed volume where we have a resonance between the loudspeaker and the eardrum, for example, which is at around 11 kilohertz or maybe a little lower if you have some front volume, then this thing starts to play a big role in what is going on inside your ear.
So basically there will be some reflection, there can be some reflections between your, and then it kind of damages the sound?
Exactly. Maybe let's maybe it's a little bit too early, but maybe we should have a little look at this here before. So if we talk about sound pressure level inside our ear, then what we can do is we can take one of those devices and put it into one of these ear simulators. What this ear simulator does is it has a microphone in there, and it replicates the impedance of your eardrum. And then you can play a sine sweep or noise or whatever on these AirPods here, for example. And we can measure what is the sound pressure level we measure in here. So this is what you would hear, basically. And then you come up with a curve frequency, sound pressure level over frequency. And I did this here for this AirPods for different loudness level, basically, or for different volumes. So 0 decibel full scale means, you know, give me the full power the AirPod can deliver, like full signal, everything to max, and then play a sine signal with which changes from 20 hertz to 20 kilohertz, but keeps the amplitude constant. But you don't get the same signal as sound pressure level in your ear. You get what the system assembly is basically making out of the thing. And this is then the curve that you would observe as a listener.
So basically, for example, this means for frequency, I don't know, 80 hertz, you would hear it a little bit louder, and frequency about 1 kilohertz, you would hear it a little bit quieter.
Right, that's right.
And so basically, when you are building headphones, then you would like to make it equal, or
no, you actually don't want to make it equal. There's many things to it. One thing is what we are used to live with is we hear the sound that is coming from the outside, for example, from a car, from someone who is opposite of us, or from a loudspeaker. And then our outer ear comes into play and changes the sound a little bit. For example, this is how you can make out if the sound is coming from the front or from the back, because it sounds a little bit different and your brain is used to that. But the outer ear we take completely out of the consideration, because the outer ear doesn't have to do anything anymore with our sound that we play here. So that's one reason why we, for example, don't want to have it flat. The other thing is people like enjoying some bass, for example, when they listen to music. Or people like to have a phone call and have the mids a little bit higher to have a better understanding, because when we talk, we are about in this frequency range here, like between the 300, 500 to the 1 or 2 kilohertz range. So you don't want to have a flat response. What response you actually want to have is a very, very big debate.
I was expecting you say something like this.
Yeah. There is some research out there from, there is a Harmon target curve. This is what a lot of people are referring to, where people started measuring or taking different headphones, different equalization, gave them to people and were asking, do you like this? Here's your equalizer, adjust so that you like it. And then they came up with curves. They evolved over the years a lot. But still, there is a debate on how to measure this with what devices. Is this like I show it here, okay? Or do I have to have a full head assembly where I plug them in? Is this really the best? Is this what the people want to hear? So there are debates outside, and yeah, I know I have seen frequency response curve from big manufacturers, how they would like to have it. And yeah, they look a little bit different. They look different from manufacturer to manufacturer, but unfortunately, here I'm not allowed to say a lot more because I got all this information under NDA. So
yeah,
yeah,
I understand. Okay, so
but you can go. There are websites in the internet where you can compare from speaker to speaker, where they have the measurements done. And you can see, okay, this speaker has more treble, this speaker has more bass, and so on. The only thing, it's also difficult to compare. If you have two people who do the same measurements with a different assembly, then it starts to get hard to compare. And we will find also in the explanations more things that make the comparison here, for example, hard. But yeah, but this is the sound pressure level over frequency that you achieve with this assembly completely sealed in here. And this is what you want to design. And now we come to the point, how do we design?
One, no, number 9.
Yeah, if you want to dive deeper into and learn more about electroacoustic analogy, we can do this as well. Maybe also for people for reference, there are a good book out there. It's in my hometown in Dresden. They did a lot of work on this in the past 100 years. But basically, this is, take it as an overview of what you do from the electric to the acoustic branch, your analogies, your potential, your voltage becomes your pressure, your current becomes your volume flow, and your capacity becomes a compliance. So basically, you can see an acoustic compliance as imagine you have a volume, and then you start compressing the volume like with a pump when you try to put air into the tires of your bike. You would compress the air, and if you do it too fast, your pump will come back to you. And this is the compliance you're working against. You will have some resistance. If you try to blow through a tiny little slit, you get some resistance. And you have your mass. The mass is a little bit difficult to explain. The easiest explanation would be you also want to move your particles. And if you want to move your particles, you have to accelerate your particles. And then you're fighting basically with Newton's law in the end. And this is force equals mass times acceleration as an analogy.
Okay, so if someone is interested in audio, this is where they can start.
Yeah, this is what some people learn at university if they learn about acoustics. And this is how you can, this is the example for a normal loudspeaker. So if anyone at home is interested in designing their own loudspeakers, you will find values for all of this in the internet for the speaker coils you want to use. You can plug this in. There are also models for that. So you can design the frequency response of your full loudspeaker, and then you can start playing. I want to make my loudspeaker double the size. Okay, so I increase the back volume double the size, and then I can see, okay, what is the pressure drop here, which is radiated into space. And this is how you can design your loudspeaker in a very easy way.
Let's jump to the next one, the number 11.
Yeah, let's design our loudspeaker, right?
Okay.
So basically what we are doing here is we are also just doing a loudspeaker design. So inside the Apple AirPod, what we find is our driver, our speaker, basically, our membrane that is moving. And let's put this here in the middle. And then we want to have a front volume. So it's a little bit disturbing, but if you look to the left, this is the towards the output, towards the ear. So the front volume in front of this, there's this volume here. So this is our front volume. And then you have those two outputs. This is where the sound is supposed to go to the ear, inside your ear. And in there, there's a mesh. So it's like if I take them a little bit away, you can see this is like a structure where the sound can go through, kind of like a fabric looking like thing. So there's a mesh placed here, and this mesh also influences the sound. You can imagine if you want to talk through a tight fabric mesh, then the sound will not go completely through. Some high frequencies will be damped. And so these are those two. And then there's another one, which is up here. And this sits in your ear as well, pointing towards your ear. So you have another one. And this goes into your ear channel. This is the front side. And then, of course, from the ear channel, this is a semi-open headphone, we call it. So it's not sealed. There are other headphones that have this little rubber sealing that you plug into your ears. Then it would be more sealed, but here you have a really open leak, basically to the outside world, to the surrounding. That's the front side. And now let's have a look at the back side. We have a volume behind the membrane. We have a mesh behind the membrane. This is actually, to be honest, I made a mistake here, so this has to go here. So we have a path between the front side and the back side via this mesh from the back side to the front side. We have the membrane, and on the back side we have a back volume. This is basically all the volume which is inside this big white thing of the AirPods, like in here. And then if you look closely, you have here some output ports, again, filled with a mesh. And the air can go through this output port directly from this volume through here to the outside world. This would be the green path down here. And there's another path. And if you look here, you see here is a little bit of an opening. And if you disassemble this further, you come in from here, and then you go through here, and then you end up at this part. So you are here. So there's a little tiny port going through here and coming out here. This is like another channel going to the outside. And then you can start to think about, why did they do this? I mean,
that's what I'm thinking about. Like,
yeah, why did they do this? They wanted to spend more money than they had. No, of course not. What you basically can do is you can shape the sound pressure that you have in the end in your ear channel by doing all of this. Let's start with the easy thing. Let's start with a mesh here at the front. If you look at the very low frequencies, like your sound pressure level is changing very, very slow, then the mesh doesn't have any effect on this. Because you can imagine you can very, very slowly blow the air through the mesh. That's not an issue. But if you start trying to blow air here through very, very fast, you get a big resistance. So it dampens your high frequency sound. So the high frequency that is generated here doesn't go directly through into your ear channel. And this is to make it a little bit more soft and easy on the high frequencies, to take out spikes in the frequency response, sometimes to shift some spikes. So to shape your frequency response at the high frequencies. Then we can have a look at the low frequencies. Imagine you pump out here also your air very, very, very slowly, but you pump it out to the big volume of the outside world. And now let's go back to the capacitor analogy. If you have the outside world as an infinity big volume, so as big as you want to, then what happens? Your capacitor gets bigger and bigger and bigger and bigger. And if you come with an AC signal to a capacitor, it will start conducting. So it will just be a short to the outside world. So all your energy will just go outside here. So for the bus response, you don't get anything here at the ear channel anymore. And what they introduced here is a leak to make this at least more uniform. So if you have your AirPod into your ear, then it will be different for your ear than for my ear, because it sits very different. But if you, as a designer, can design what leak you want to have, then you plug in here something that like defines the leakage you get. And this is why they also defined here a leak. And the second thing is I can, via this, also control, I can give a feedback loop. You see here, you have a path between the front and the back volume here, and I have another path between the front and the back volume here. So I create two feedback loops. And now we get to what does your loudspeaker do? If you drive your loudspeaker in free air without any load, like you just take it in your hand and you drive it, it will do whatever it wants. It will vibrate like hell, especially in the eigenfrequency of the driver. And what you want to do is you want to dampen the driver a little bit. So what you can do is via the feedback loop, you can put a back volume, and you can create via the shaping of this a damping to your driver. And you can also do the same thing with the mesh in here between. So you create another path which you can use to equalize between the front and the back volume. And depending on how you design this mesh, it's basically a filter between the front and the back. So you put a filter in parallel to your source, and therefore you can shape the frequency response. And so this is basically what this is doing. And the second thing is, especially for the back volume, you want to load your speaker with something. If you load your speaker just with an infinitive big air volume, as I said, your speaker does something different than what it would do if you load it with a very, very tiny volume. Imagine you would have here a closed tiny volume behind your speaker. Then the speaker couldn't move at all because it would have to compress this little tiny volume. And designers use this in the application to define the load to your membrane, because they cannot really define what is going on with the leakage in the front. But for the back, they can define what they want to have there. And so they use it as a defined load to the membrane. And as I said, you have those filter versions. So our channel back here, we have one channel here, which is just the mesh. We could say the mesh is just a resistance, but we can also put this little port, and this little port is kind of an inductor and a resistor. So we can also tune the eigenfrequency of this port and of this thing. And so we can start tuning the frequency response of our whole assembly. And taking all of this together is where we end up in the end with the frequency response I've shown.
Okay, this is going like really far away from my area, but basically,
basically this is maybe something you understand better, because this is exactly your area then.
Yeah, but
so
let's go back. I have few questions.
Okay.
If I understand right, because my first question would be what I had in my head. Like, you are talking about filters and these kind of things, but theoretically you could do this in DSP, no? In processor, you can create any filter you want. But this is kind of like mechanical filter, or that's the difference?
This is kind of mechanical filter. You could create in DSP every filter you want to, but especially you have to think about first power consumption. You don't want to have so many filters, especially real-time filters in your DSP. You have to think about latency. And you have to think about, you still have a mechanical system with resonances, and having even a DSP with filters, you don't want to filter all of these resonances away in like using a DSP. If you can do all of this analog without having any effort that takes energy consumption and so on. So yeah, you do all of this. And nowadays, like 10 years after this design, you are right, you could do a lot of this, a lot more of this in the DSP. But then there's another thing coming, and this is noise cancelling, active noise cancellation. And for this, you want to be fast, you want to be linear phase, and then again, you start doing all of what you can do in analog world, to not have to do this via your expensive and power-hungry DSP.
Okay. So basically, this is very important, especially for this kind of device, because it can save power.
Yeah, so this can save power. can save also headache. As I said, like let's just, for example, let's take our resonance, which we have been talking about between your eardrum and your membrane, like the air between. Say I put it in and my resonance is at 8.5 kilohertz. Then you put it in and it's at 8.2 kilohertz because the ear channel is slightly bigger. What do you do with your DSP? You would have to introduce a feedback microphone and start tuning your filters, putting notch filters in there and so on. So this gets very complicated very fast. But what you can do with this, you can just add damping to your membrane. So you're not that concerned about like shifting the eigenfrequency a little bit. And you're also not concerned about your filters being unstable. This is also a very big thing. Especially if you start about talking about feedback, say we want to do A and C, and we have a microphone in here, and we sense what's going on in here, and then based on what we sense here, we want to adjust the signal for our membrane. We have to make sure this is not self-amplifying because this could damage your ear very easily. For example,
that's what I was thinking about, like, because when you say about these resonances, that's what people can hear when you take your speaker and microphone and you put them closer.
Exactly.
So basically something like this could happen in your ear because the channel is like super small, and then the frequency just could. And
if you put in the microphone and you build your feedback loop, yes. This is a big part of active noise cancellation. So maybe let's just have a sneak peek here.
Okay.
Because I think this is not in the AirPods, but I think this is interesting to many people. Everyone is talking about A and C. Some people refer to it as active noise cancellation, and some people refer to it as active noise control, and a lot of people mix up the two and take it for the same. We are developing right now from noise cancellation to active noise control. So imagine you are sitting in your plane, then the active noise cancellation is trying to get the signal that is coming from the plane, from the surroundings, and just take it away. Active noise control takes this a little bit further and says, okay, there's someone talking to you. I just damped the surrounding of the plane, but I don't damp the speech. These are those two terms.
I can see this difference actually between my old, I think like Bose phones, and comparing to new Sony headphones. Like with Sony headphones, I can actually hear everyone who is talking, even if the noise from the airplane is gone.
Yeah, and for this you have different things that can help you. One thing is from the outside world, there's a noise coming that you don't want to hear. What you can do is you can use like on ears or over ears, as I am wearing them right now, so that you basically physically block the sound signal, so it cannot penetrate through the headphones. That's the one thing you can do, but still it will be able to penetrate through the headphones. You have those opening, you have those back volumes, you have those leakage and so on. And now what you want to do is you want to measure what noise is coming, and you want to create like the 180-degree phase shifted signal to cancel out the noise, sadly. And therefore you can have multiple approach. The oldest approach, or the first approach, is basically you put a microphone in front of the speaker in your ear channel, and then you say, okay, take away everything in here that doesn't belong to the audio signal that I want to play. So you basically create a feedback loop in here. This is working very well if you think about, for example, helicopters, where you can put like a notch filter on your signal coming from the rotors, because it's the same frequency all along. And so you can say, okay, I have my whatever 200 hertz signal. I can lock my algorithm to it and put the 180-degree phase shifted signal to it, and I'm fine. And for this, I also have time, because the signal is a stationary signal, it stays. And now you also want to cancel, for example, noise coming from the outside. This is much more difficult because you have to really adapt to the signal that is coming from the outside. You cannot just add noise, because then you would just double the signal because you don't have the phase information. And what you can do is you can put a microphone also to the outside. And then you get the microphone signal, and then you have a few microseconds time until the wave is basically on the same area as your speaker to, in this time, produce the right signal and give it to your speaker. And this is very, very demanding because I wrote it down here. If you have 2 millimeters of distance, that's 6 microseconds of air travel time. And to, you know yourself, to have a microphone digitized, put into a DSP, have a filter applied to it, and have it then played back on an amplifier, 6 microseconds is hard. But this is basically what the feed-forward ANC is doing. And this you can also combine to a hybrid system, and this is what the modern headphones are doing. Like they have both, and they combine the information out of both and do both. And if you design such a system, say we have from the outside world a signal coming in here, and say here, my thing doesn't work right, my filter is not working right, and the phase shift doesn't apply, then it's exactly what you said. You have your microphone directly in front of your loudspeaker, and you get this feedback loop, and it's a self-amplifying system. So there's a lot of research and a lot of work, for example, only in the stability of these algorithms. And here I'm not talking about energy efficiency, and I'm not talking about the incredible speed you need. And then you also have to have the phase response of the whole system right. And the loudspeaker has a resonance at 1 or 2 kilohertz roundabout. So your phase shifts from 0 to 180 degree in this range. So you have to compensate for this or take your loudspeaker and shift it to a higher resonance frequency. But then, you know, higher resonance frequency is a stiffer membrane, and the stiffer membrane doesn't want to vibrate so easy. You have to have a bigger membrane, a smaller membrane. You need to move it further, and then it gets nonlinear, and you're in all these design conflicts. And this is a really tricky part to get really right.
Interesting.
And people achieve 40 decibels of noise reduction. So, you know, you come here with 1 Pascal, and we get like times 100, like 10 millipascal of noise left here. This is crazy.
But this is something similar to what I was expecting how it works.
Yeah. And it works especially for the low frequencies very well. It works very well if you can put your microphone very far from your ear. That's why over ears have a much better noise cancellation than the in ears, because, you know, the timing gets stricter. Over ears can also have the insulation, just the physical insulation by blocking the outside world from your ear.
So theoretically, you could delay it even a little bit more.
Yeah. So this is a really big topic. It puts a lot of demand on the acoustic system because it should be like linear phase, because you then don't have to deal in your filter with your phase response as well. It's a crazy topic to work with.
Okay, let's go back to
the easy stuff. Let's go back to the easy stuff.
So you said I'm going to understand this one, not really.
Yeah, I think you understand this a little bit better. So what I did is what we had before, like this assembly, I transferred this into electrical schematic. And what we are interested in, we have our speaker. What we are interested in is the sound or the pressure drop, like the voltage drop here.
Mm-hmm.
And now you see what all of those things are doing. Like they are just little RLC filters you apply to the front side and back side. And by doing this, you can shape, of course, the transfer function from here to here. And this is why they have all of this in there.
Mm-hmm.
And yeah, that's basically how it works. And if you, as an acoustics guy, you disassemble or you think about one of this, you start taking this and transferring this into that.
Mm-hmm.
Because that's the easiest representation. And then once you're done with this, you start your FEM simulations for the high frequency things and for the resonances and for everything that's above 8 kilohertz and for everything that's like thermoviscose signals that come into play, like your air gets also hot and cold when transferring it through meshes and all this stuff. But this is, I think this is far above the scope we have today.
So how, I have only one question. So how do
Sure.
they know how to design this kind of mechanical filters? They have to simulate everything, I guess, and maybe there are some kind of like standard structures. Like, I don't know, when you design antenna, then you know approximately like this kind of shape will do this.
Yeah.
Okay.
Basically, what you can do is, for example, I want to know what volume I have here, or if I know the volume here, I can calculate the value for this capacitor, or the other way around, of course. If I know the value of the capacitor I want to have here, I can calculate what volume I have to put. The same is true for the channels. For the channels, if I know the length and the width and the height of the channel, I can calculate those two values.
Okay, I understand.
And yeah, the other way around. And then I start playing and doing all of this until I'm happy with my frequency response.
Okay, I understand.
If there would not be like a system architect telling me, no, you cannot do this mesh because we have to be sure that water doesn't penetrate through here. Because I'm like, okay, I want to have a very lightweight mesh which lets through all my sound. And then someone is coming and telling you, no. Water, dust, and so on have to be kept out. So we
I just dropped my headphones yesterday to, I had a glass of water and I was running somewhere. I just put them down and they ended in the water.
Oh, and they are still working. So it worked what they designed. So yeah, but that's basically then the constraints you also have to like live with. You have to live with the volumes that the electrical designer leaves you after he puts all the PCBs in there, and the industrial designer leaves you after he finishes the outer shape of the AirPods, for example. And basically that goes hand in hand. And so that's how you basically design those things.
Okay.
And once you
okay, go ahead.
Yeah, once you have designed it, also you start checking with FEM in the end, like with acoustic FEM. So you simulate your speaker, you simulate your volumes, and you basically run big models on this.
What kind of software do you use for this? Can we go on website and just show one example?
The main software that a lot of people are using is Console. Or basically there are many softwares, but yeah, one popular one is Console. This is a multiphysics software where you can have your electrical, your mechanical, and your physics domain in there, and can simulate all of this. In the past, you can use ANSYS. There is also acoustics module. Acoustics.
I didn't know they have this. Huh.
Yeah, so they have an acoustics module, and there's many more like LMS and so on that you can use for this. From my experience, I'm not paid by a Console, but they went ahead in the last years, especially for those like small consumer products like headphones and so on. Yeah, but as I said, there are more software you can use, and there are also like Console IEC 711. This is the ear coupler we were talking about. So this is the part we plug in the end to simulate what our eardrum is doing. And for example, they have a example how you simulate this ear coupler. Here they show, okay, you have your ear, inside you have your ear coupler. You can model this. This is basically how it looks in the inside. You have one big volume and two smaller volumes coupled via tiny slits to reproduce the acoustic impedance. And then you can model it, and then you find the characteristic impedance of the ear channel here. So this would be like the impedance, and you also see the for different models calculated, but this is the one that is most comprehensive. And you see at 11 kilohertz, 12 kilohertz, you see the big resonance there, which I was talking about. And now if I put an additional volume in front, additional capacitor, additional volume, your frequency shifts a little bit down and you end up with like 7 to 9 kilohertz in your real assembly. And then you can also, for higher frequencies, 25 kilohertz, see that you have a wave in there, like a pressure distribution. And if you go to the low frequencies, you have the same pressure basically everywhere because your sound wave is so long. And that's basically how you then, start calculating all those things. And here you have losses, as I said, the resistance here. If you want to blow through a tiny opening, you get losses. You can calculate this, but then you have to do the thermoacoustics thing, because the loss is the heat. So the particles will heat up the area and the air here, and this dissipates basically the energy. And this is how it works. And if you want to play around, get one of their, for example, free seminars, and you get a 2 weeks license, and start playing with all of this and have a look, and you can model all of this.
Let's go back to our slides, because we need to be a little bit faster. I think we are running out of time. I'm telling you, I had no idea. It's so complicated.
So but then if we are running out of time, I think we should let's have a look at one very easy one thing to understand, for example.
Okay.
And this is what happens with leakage. So what you see here is SPL, or sound pressure level over frequency, and you see your frequency response here. And then what I did is, I opened a little port to the outside. This would be like if they are not sitting 100% tight into your ear, and I opened it further and further. And then you can see that with increasing leakage, your low frequency response goes down. And this is, for example, if you buy such an earphone that is not a closed, not a sealed system, not a closed system, it's hard for them to have a good bass response, because this would be more what you are looking at or hearing. For example.
So lower frequencies, they actually escape, they go away.
Yeah, at like 500 hertz, 600 hertz, the effect is basically gone. And below this, you get drop of like 40 decibels, which is huge. And that's what I also said. Like if you look at how people reviews and so on, I would show you a review of this AirPod. And I would show you this blue line, which I have measured, no issue. And then you buy it, and then this is what you really hear, because it's not sealed in your ear. And these are the little tweaks you have to know if you want to trust a review, or at least know what you want to get out of it.
So next time you have to cover your ears when you are listening.
Maybe, or buy a closed type, for example. If you love this bass, you buy a closed type with one of these rubber thingies, because this seals your ear. Basically, here's also a little hole in there to have some leakage, but for the expensive ones. But okay, and the open type would be the opposite. They are ones completely open. And if you want to have phone calls, you don't want to have this. This just disturbs. If you're walking, for example, then this disturbs you a lot, because you hear the sound of the walking. Close your ears with your hands and run through the corridor. It will be really loud in your ears.
That's interesting. This is maybe a little bit different topic, but once I bought quite expensive headphones like this, small, and always when I moved and this scratched somehow, it was all going inside. It was horrible. It was like $100 headphones, and I was like, horrible.
Let's talk about the $10 headphones, right?
Sorry?
Let's talk about the $10 headphones then. I got my hands on some.
Okay. So these are not the real ones.
These are not the real ones. They were broken. The electrical engineer sees here a little line. So here we have a broken component. That's why they were not working anymore. But I mean, I disassembled them, and you see what's in there, and then you compare what to. Even though it's an AirPod Pro, but I can also tell you the AirPod Pro doesn't look like this. So it's really just a battery that was not protected in my case, so you have to be careful. You have a speaker, and you have a board with a chip which is made for headphones basically, and you have the reference circuit on it.
Okay, so basically this means they only look similar, but they have nothing to do with
Yeah, except that the white apple
engineering.
on it, they look similar. Yeah. So
They have Apple, right?
yeah, I see.
Yeah, I can see it.
Yeah, they have Apple on it, and I would not. I mean, if I put them next to each other, you see little things. But if you give them to me and tell me, you know, they are Apple headphones, they have also a case and so on. They look exactly the same.
Maybe you can weight them.
Yeah, maybe.
Or maybe they put their extra weight so they weight same.
or you just listen to them and you know.
Yeah, but
Yeah.
I wouldn't know if you only buy one, you wouldn't know how they should sound.
Right. That's true.
Okay, we still have some time. So what else we can talk about?
Maybe what we can talk about is this, because I think this is also interesting to a lot of people. We have two microphones in there. They are sitting behind those two holes. And if you want to play with those microphones, you can buy just eval boards from SparkFun or whatever and plug into your Arduino and have some fun. And then they are already assembled on a little PCB. But since I know a few things at least about MEMS, I thought I'll crack them open and show you how they look from the inside.
I'm curious.
And what you build in is this little can. This is 1 millimeter by 2 millimeters. And inside this little can, you'll find a MEMS microphone.
So what does it mean, MEMS?
MEMS does mean you take a silicon wafer, like the same, not exactly the same, but let's say the same wafer you take to build your CMOS chip or your ASICs and stuff. And what you do is you don't build transistors and you don't build logic. What you build is a mechanical system. So you deposit layers, you etch layers, then you deposit other layers, then you etch them again, and so on, until you get to a mechanical system, which is like kind of shown here. So what you do is you take your wafer, your base substrate, which is a few hundred micron thick. This is also the wafer. And then you start depositing an electrode, for example, from polysilicon. Then you start depositing a insulator. And then on top of the insulator, you deposit another electrode. And then you start etching away your insulator in the spots you want to etch them away.
It can vibrate, it can move, basically.
So you have a you have a 1 micrometer. It's not exactly 1 micrometer, but for a good thumb to, you know, think about thicknesses, say this is a few hundred micrometer and this is about 1 micrometer. And this is a very, very thin membrane. And this is basically this here from the bottom and this from the top, and this can vibrate. And when you start coming with sound from the bottom, you vibrate this. This doesn't vibrate because it has holes, so the sound the air can just escape. And if you read this out as a capacitive sensor, you get the sound signal out of it. And you know, you have two of them in your AirPods, and to build only this system, you know, it's maybe as much work, maybe not so much work, but it's a lot of work of many tens or hundreds of engineers and many years of development to build just this system. And then you build this system in such another complex system. And this is where we are at engineering today, basically. And you have two of them. One is here with the little opening here. You have to have a soundboard, and one is on the bottom. And as I said, you use them for example, for phone calls. So when you have a phone call and you talk, the air is coming from here. It's coming first at this microphone, and then a little bit later at this microphone. And then you can do a correlation between the signals. It's called beamforming. And then basically have only your voice amplified and not what is coming from here, from the outside, from your car or other people talking, for example.
And I think, yeah, go ahead.
Yeah, go ahead.
I wanted to point out, I think last time when we talked together, you mentioned this kind of technology, it can be used for all the kind of sensors, even like the accelerometers, they work basically same way, or what else can be
Right.
MEMS?
Yeah, the accelerometers are MEMS as well. They are built like in the same way, just that you don't have a membrane that deflects. It is more like a structure that is hanging on a few springs and deflects in this direction and up and down, and then you can read it out. You can have gyroscopes that can detect rotations. You can have basically all kinds of different things you want to build as usually capacitive sensors in such a small way. They are not in the AirPods, but if you think about your mobile phone, for example, in your mobile phone, you will have a pressure sensor, which is built as a MEMS. You will have microphones that are MEMS. You will have accelerometers, gyroscope, magnetometers, and I probably forgot one or two. So you can also build this on this platform. And the thing is, it's very, very small. And if you have a high volume, so a high number of sensors you want to produce, it's very cost effective.
Mm-hmm. And so I think you mentioned you used to work with these, or so what is your background? What do you do actually?
So my background is that I studied acoustics, electrical engineering and physics, and then I did a PhD on CMAT. CMAT is basically a MEMS sensor and transmitter that is kind of looking like this, like a microphone, but it's working in the ultrasonic range. It can transmit and transmit and receive ultrasonic waves. So that is where I did my PhD in. Then I worked a little bit in automotive and failure detection. And then like a few years ago, after I went working on ultrasound, on normal ultrasound sensors in industry, I went back to the MEMS. And in a startup, I joined a startup that developed MEMS loudspeakers. So basically the loudspeakers that will be in here in future generations, or I cannot say if they are in here. I hope they will be in there in future generations because the startup got bought by Bosch. So Bosch is now taking this further and producing those loudspeakers. I worked with Bosch for a longer time, did the system engineering for the loudspeakers we were producing. And I hope in a few years they will be so far that they can release them and have them like in the mass products implemented. So that's what I basically did in my past career. And now I'm self-employed and I'm helping especially smaller companies and startups to get their products running, get their sensors in line, get their system engineering done. And not fall into all the traps and software engineering and electrical engineering and so on that I have had in the past.
You have a website, yeah? Do you have a website?
I do have a website.
So if someone is interested, or if someone is working in this area and they need some help, maybe.
Yeah, if someone is working in
you.
this area and needs some help, you can find what I'm doing on my website. And I also released just if you want to learn more about, for example, the AirPods, some of the information I had, we have talked about, I have in an article you can find here. If you want to learn about other things I do, just go on my website or just contact me and feel free to have questions or remarks, comments. I'm happy to learn new stuff every time. So feel free to contact me. And if you have the need of helping a product in like a fast and structured way and not doing loops and not making a lot of mistakes, you can also contact me and I will see if I can help you.
Okay, we can go back to the slides. So what else is interesting, what we can talk about? Because we may have, I don't know exactly how many, maybe 10, 15 minutes, I don't know.
Okay. one thing we didn't talk about is, for example, the THD, and everyone is talking about THD, total harmonic distortion. Total harmonic distortion means I have a signal, say I feed in a signal at 100 Hertz in my speaker system. And what the speaker system does, it does something with the signal and gives me a sound pressure in the end. And the sound pressure will not only contain the 100 Hertz signal, it will have some noise, and it will also have some higher harmonics. So you will have signals at 200 Hertz, 300, 400, 500, and so on. And if we go and take the energy of our signal, subtract the fundamental and divide it, so we get basically the rest divided by the fundamental, we get the THD. So the THD means if the THD is, this is in percent, 1%, 1% of the sound signal that I measure is not what I intentionally wanted to give into the device. So this is a measurement you do a lot of in acoustics and also in electrical engineering. And what I have here is 3 curves for the THD of the AirPod. And what you can see is they are curves at different dBFS, dB full scale. So that means this is full loudness, half of the full loudness, and quarter of the full loudness. And you can see that we get different THDs. For the blue one, which is the minus 12 decibel, here's a minus missing, minus 12 decibel full scale. The minus 6 decibel has a little bit more THD, and then you have the 0 decibel, which has the most THD. And you can see a couple of things. First, it rises, of course. The higher you make the signal, the more you get non-linearities in the system, especially in the mechanical system. And you also see the 2.5 kilohertz peak in here. And also a little bit, but maybe that's 2.3, and that's 4.8 or so. So you see that the nonlinear cone vibration, or I suspect that this is the nonlinear cone vibration, does some things. And produces nonlinear excitation about the resonance of the driver. And you can also see that, for example, because this rises so much, this is an indication that the driver has a inductor in the back and moves over a magnet. And here it seems like it has the range of movement is done. So we are moving all the range it can do. And if you want to move it further, then it gets nonlinear. And this is also why you get some THD. And this is a good way on judging if a speaker is good. For if you buy a top-end speaker, this shouldn't be any concern, because I guess under 1% here you cannot hear, and here under 0.1% you also cannot hear. This, a very, very good trained ear would be able to hear, but if you hear at 110 decibels this THD, then maybe your ears are also blown away already, because this is really, really, really loud. So then you don't care about this anymore. And it's also used in testing the device a lot. If there's a little error in here, if there's something, I don't know, some fracture here in the cone or anything, then you see this in the testing. And there's also a reason why the cone is looking like this. Usually you could say, okay, you just make a flat membrane and attach on the back a coil. But what they did here is they have a metal in the metal membrane, or there is metal on top. It's not full metal, but there's metal on top on the center and not on the outer core. And they have those rings for stiffening. And this is all made first to have the resonance damped of the speaker, but also to have the cone not doing nonlinear higher mode vibration. Like say a higher mode would be this moves forward, and while this is moving backward, because you have the higher order vibration of this mechanical device. And this is, for example, what people specify if they want to have a good speaker inside their device.
So if I understand correctly, it means you send 100 hertz signal into this, but it will not only produce 100 hertz, but it may produce also, I don't know, 2.5 kilohertz.
Yeah.
Okay.
Right.
And do you do
And
this for all the kind of frequencies, or 100 hertz is
yeah.
like standard?
Yeah, what you see here is basically done for all the frequencies. So you do it for all the frequencies, and basically you do a sweep, and from the sweep you compute all your frequencies back. And if people refer to sometimes you read just the device has 0 point something percent THD, or the device has whatever decibel SPL, then acoustics people refer usually to the 1 kilohertz point here, because in the past this is 1 kilohertz, 1 Pascal is 94 decibels. So usually people refer to the 1 kilohertz and normalize everything to 1 kilohertz.
Okay, but
so
now
if you would ask me, if you would ask me for a THD value, I could tell you, for example, okay, for the maximum loudness of the device, I could either tell you 0.03%, because I'm sneaky and I'm from the product management or from the marketing department, and I picked the 1 kilohertz line. Or I would be an engineer and I'll tell you, okay, this is the 0.5%, for example.
Okay, so just if I understand right, because now I'm a little bit confused. So originally I thought when you play 100 hertz, this is what you measure, but that's not what you measure.
No,
you have to play it for every single frequency, and this is what you measure?
So to get this graph, basically the easy way to do how there's let's explain first the easy way. What you could do is you play 100 hertz, you measure what you get, and then you say, okay, in this case it would be 0.5% of my signal don't belong to this signal which I intended. So my value would be 0.5%.
Okay.
Then I do the same thing at 200 hertz and so on.
Okay, I understand now.
And in practice, to not have to play like thousands of signals, what you do is you play a sine sweep, and then you decompose this basically. So
basically these are telling us how this speaker will play the frequencies relative loudness for like same signal, but different frequencies.
Yeah,
same amplitude, but different frequencies.
Yeah, and say for example you want to listen to a 100 hertz signal and it has a very high THD, then you will not just hear the 100 hertz, you will also hear the 1 kilohertz, which is bad because you don't want to hear the 1 kilohertz.
How do you know from this graph you will also hear 1 kilohertz?
In this case, you will not, but you will maybe hear 2.5 kilohertz.
Okay. That's now I understand now. So, okay.
Or another word, which is also not true. The true interpretation of this graph would be if you play 2.5 kilohertz, you have a very, very high THD, which tells me that I will not only hear the 2.5 kilohertz, but I will also hear 5 kilohertz, 7.5, 10 kilohertz, and
Harmonics.
so on. Yeah, harmonics and also noise. Like here, I will more hear the noise. Like if the signal here becomes more noisy, then it's mostly not the harmonics, but the noise.
I understand.
And if this is very, very low, then I will hear exactly what I make the loudspeaker to play. And if it's very, very high, then I will hear something else.
I understand.
Exactly.
So everything is new for me in this area.
Okay. So maybe let's disclose. I think this is a good point to end the thing in the terms of, let's just start thinking once again about why all of the things are in there and how they are implicated or built in there. And I picked also some funny or some like not really obvious things. For example, we have the AirPod, we have a speaker that has a magnet in the back, the speaker itself, and they use it to hold the AirPod in the magnetic case. They have a magnet in the case, and so this is a functional integration of those two things. They have the battery in the stem because of the size. but also to balance the weight.
Yeah, I was exactly thinking actually about this. That's why, and it's also long because it's antenna.
Yeah, right. They have a meshes everywhere, not just to do the sound quality, but also to protect against dirt, water, and so on. And maybe one more word here. Those meshes, they are really expensive and really complex materials. They are, you have sometimes Teflon on top and all of this. There's a lot of engineering behind just one of those meshes to keep the water out. I called it flexboard or flexboard origami to assemble the flexboard in here. We have the PCB, which I found a clever thing. They wanted to glue the speaker on the PCB, and they used this for test points because they cannot put components there because they want to glue something there. So they put the test points there. And also they glue parts in place. But this is also one thing, not just to annoy you that you cannot change anything, replace the battery and so on. If you don't seal this with glue, the thing will not sound well.
Because there may be different resonances and vibrations or...
Yeah, and leakage, air leakage to the outside and so on. And on the other hand, they went to have all the way. We have an accelerometer for tap and speak detection or for motion and speak detection, basically. So they put 2 accelerometers in there. They put 2 microphones for the directional beamforming things. They have here dedicated chips for the single elements because this was new at that time and such a device, so highly integrated. They have 2 sensors to even see if it's in your ear. They have especially meshes also in there, not for the outside, for the water, but also really to control the characteristics. And they even made an extra hole out there with a mesh to control the characteristics. And they went for a very, very large speaker where you can have a lot of displacement, which is good for those open designs because you can, in the bus area, compensate more for the leakage. And all of this thing is integrated in here, and there's so much more. And I find it so fascinating.
Is the sound really so good? Because I really didn't want to spend so much money on buying this. I think
don't buy AirPod 1 or 2. This is old. The sound was maybe good for what it could do like 10 years ago or 7 years ago. But you don't, this type of earphone, you don't buy for sound, you buy for usability. You buy to be able to not have a cable, to not have, or to be able to make phone calls, to integrate with your other Apple devices. This is why you buy this. If you, this is not true for the new AirPod Pro, for example. They are much better than this, what you get in sound quality. And I think this, what we see here, is in sound quality not comparable to the new devices with ANC and all this stuff integrated. So there's a huge leap in the last 10 years.
I only ask because, I was always like, it only lasts like 2 hours. And, I know my wife, she sometimes, when I went to some exhibition or some conference, they gave us, of course, not these AirPods, but something different. But once it discharged, like in 1 or 2 hours, she never charged it again. And
so, yeah, it depends on what you want to. If you want to listen to very, very good, high quality music, you don't buy those. You buy 2 very good loudspeakers and put them in front of you. If you want to also still listen to very, very good music, but don't want to have 2 big loudspeakers in a dedicated setup, you buy over-ear headphones. If you want to have a small system which you can take everywhere, it's not clunky, and still want to have ANC, you buy in-ear headphones, like those new TWS headphones. And so this is basically, some people don't like in-ears because they don't like stuffing things into their ears. Some people don't like over-ears because they have difficulties with the glasses. And I mean, there are other good manufacturers as well. So I would not judge which one to buy. I even don't know myself. And
I
every
had to
year
ask
there's new
this
ones
because
coming.
you just explained there is like so much thinking and so much like theory behind all this. So I was like, okay, like
Yeah,
it must be really super cool and
yeah. No, there's two reasons why I picked this one. First, it's quite old, a little bit bigger, easy to get, and that's why it's easy to explain what the parts are doing. And the second thing, the new ones, they are even more sophisticated, higher integrated. So it is just for explanation reasons, this is easier to deal with. And for a headphone enthusiast who's working in this, I think they know most of this. But I think for most people, like for you, for whom it's new, it's a lot of information, and
it
that's
was
why I picked
it was
those.
very new. I'm telling you, before we started this recording, I would be like, okay, so I just place there some battery and I don't know membrane and that's it. Like I would
Yeah,
not be
yeah.
thinking about all the channels and feedback and front
So
volume and
you
back
would build
volume.
this, right?
This is exactly what I imagined. Yeah, this
Yeah,
is exactly.
yeah,
Uh,
exactly.
okay,
Yeah,
okay. Thank you so much, Markus. This was very, very interesting. I learned a lot. If anyone has any special questions or any kind of questions, they can leave them in comments. If maybe someone is interested working with you, or if they have some kind of project what you could help them with, then they can contact you directly. Thank you very much, Markus, for this.
thank you so much, Robert.
And that's everything. Thank you very much for watching this video. By the way, we are preparing some very interesting tutorials, so if you don't want to miss them, hit the subscribe button. If you want, you can also check out our Fedevel online courses, where you will find everything important from basic board design up to advanced hardware design and PCB layout. The link is in the description. That's all for this video. Thank you again. Don't forget to leave your comments and see you next time. Bye.